Hi, in this video, I'll be going through some applications of differentiation and how we will be using differentiation in multivariables. So one of the applications is known as the linear approximation in multiple variables. So recall that in calculus videos, I went through how do you linearly approximate a function in one variable. And really, you're just taking the gradient line and you're using this point as the approximation point. So we have a similar idea when we have two variables now. And for a sufficiently small interval, we have that the function of a plus h comma b plus k minus away fab will be the derivative plus a error term. And so this derivative now we already know it's going to look like partial f with respect to x times this h and fy times k, because we know that the total derivative is a linear map in the form of this. So in other words, we can state that the tangential plane by bringing this over is approximately f of AB plus this linear map, this total derivative. And that really coincides with the ideal and geometric picture that we want to agree with. And so, we'll be moving on now to something very important and very useful known as the chain rule. And the chain rule, if you recall in single variable calculus, it means that if W equals to f of x and x equals to g of t, then so W will go to W will be in terms of x, will be in terms of t. And so to go from W to t, the derivative will equals to dw over dx times dx with respect to dt. And we of course have the analogous statements for the chain rule in multiple variables. For the proof of that, I'll leave it to you to read the textbook or online notes. But it basically makes use of the mean value theorem, like how we did it for the first variable, for the one variable case. So now I'll just state the chain rule, and if you want to prove, you can just read it online. So for now, we have two variables and one independent variable, meaning x and y are the intermediate variables, we call it, and they are related. They are in terms of a single variable t. So while z is a two variable function, it can be reduced to a single variable function by substituting x and y for gt and ht. And as a result, when we want to differentiate f at a point, we can just say that the dz dt. So you use a solid D when you know it's in one variable. So it can only be the derivative can only be in that variable. Later we'll see when we use the partial z. So this is dz dt will equal to the partial z over partial x. And now the reason why we use partial here is because z can be broken down into x or y. But if it was broken down strictly into t, it's only one variable. So we say that it's the partial z times the partial x of dx dt. So this will get you the partial, in a sense, the partial z with t when you're talking about the x side. And then this will be the one with the y side. So the diagram illustrates the following. So with x, we need to partial it with x. We have z, we want to partial it with x first to get into this case. Then to get into t, we just need to times dx dt. Similarly, we here partial into y, then we times dy dt. And hence we have the following. So we take a look at an example. So x equals to x squared y plus 3x y to the power 4. And we know x equals to sine 2t and y equals to cosine t. Then we want to find dz dt. Well, we just do our chain rule and we just take dz dt equals to the partial z over partial x times dx dt plus partial z over partial y times dy dt, and partial x to partial z differentiated with partial x will be this following, and dx dt is this, and for partial z over partial y it is x squared plus 12xy cubed, then you times minus sine t, and so we are done. So you can see the chain rule isn't very hard to apply, and the proof, while a bit more complicated compared to the single variable, is still very easy to follow. But now we just really need to take note and remember this formula. And now we want to extend it out to even more variables where we have two intermediate, so x and y, and also two independent. So x is in terms of g and t. So s and t, I mean. So in this case now, when we want to talk about the derivative, we cannot have the z ds anymore, because z can be broken down all the way to two variables. So if we the s dt, we have to use the partial z and partial s, because z can also go into all the way into t. So you should really remember how to use this diagram to help you. So now we can only use the partial z with partial s, but it is exactly the same case over here now. So you just need to use partial f over partial x, which we already know breaks it down. And for x now, because it only can be in partial form, we can only go into partial s. So similarly, we need to add the component from the y side, and we're done. So if you understand this diagram, then you understand how this formula comes about. And with that, we'll take a look at some example to reinforce our understanding. So we have z equals to e to the power x times sine y, and x and t and y are the following in terms of s and t. So when we want to find in terms of partial s only, we just need to take everything, all the s components, and we want to find in terms of partial t, we take all the t components, and you can work it out yourself and see that this is the following solution. So in general, when we have a function in terms of m variables, and each of these is in terms of another m variables, then when we want to go into one of these m variables, so we get partial u over partial ti, you just need to take partial u over each of the n variables, so there's n of these, and each of the n you just go into each subcomponent, and really if you illustrate it with a diagram, you'll be able to see it clearly. So this is the general chain rule. Lastly, I'll go through what it means for implicit differentiation in multiple variables. So in one variable, we know that sometimes we are unable to simplify our variable into a single term on one side. For example, ey sine y equals to x. You cannot get y in terms of strictly x. So some function of strictly x, because this part you can't break it down. But what you can do is you can implicitly differentiate it, and we have the same idea. So now we have multiple variables. So we want z equals to something gx plus gx comma y. But sometimes we're unable to do that, and so we create a relation in the same idea. We now take a big function where it relates f, y, and z. And if we are able to write z as a function of x and y, we can also say that this function defines z as a function of x and y implicitly. So we can take note of this following. So x can be written as this for our upper hemisphere, and z can also be written in this as upper hemisphere. And so we can say that f, this relation, defines the z implicitly. Similarly for x and y. And because if we are able to define something implicitly, then for the one variable case, we can let f equals to x and then y is fx. Then by using a chain rule application, we see that if we differentiate this with respect to x, the f of partial f, capital F of x times dx plus capital F of y times dy dx will equals to 0, because the derivative of 0 is 0. This part, well, dx over dx equals to 1, so it's just partial x of capital F. And then we just bring things over, and you see that the dy dx equals to minus fx over fy, which agrees with what we have already done for implicit differentiation in the calculus series. So you can just take a look at this example and its solution to ensure that you understand how do you do it in one variable first. And now if we have multiple variables, we can do the exact same thing and use the chain rule again. But now we just need to remember it's partial x and partial y's. And so we see that partial z over partial x will equals to minus this implicit function over derivative with respect to x over the capital F with respect to z. Similarly for partial z over partial y. So I hope implicit differentiation is clear to you and you remember. So it is really basically just taking an equation and you just apply the differential operator throughout. We shall take a look at this example that will illustrate how we can actually use implicit differentiation. So it is calculating the tangential planes, and we know that in the tangential plane, the tangent vector to the positive x direction will be 1, 0 and partial z over partial x. As for the y direction, it will be 0, 1 partial x, z over partial y. And so the normal to this plane will now be taking this and this cross product together, and we get this formula. And so now we want to ask ourselves how we get the partial z and the partial y. Well, we now, that will be the hard part of the applying, using this formula of calculating tangential planes. But if we know implicit differentiation, now we are given a weird formula. Instead of letting z equals to the square root of 2x squared plus y squared, we can just implicitly differentiate this equation by just taking the operator of one of partial x. So we differentiate with respect to x and we see that we get the following. And so then you bring over and you get dz dx in terms of x and z. And partial z of partial x evaluated at 1, 1 square root 3 will just be 2 over square root 3. Similarly for y, you can do the same thing and you get that partial z over partial y evaluated at 1, 1 square root 3 is 1 over square root 3. And so the equation will be the following. So you can see how implicit differentiation is really useful, especially when you are unable to get the variable in terms of a singular explicit function. And instead you can just apply the differential operator when you're able to recognize that the equation can be written in implicit form. And this allows you to help you calculate the tangential plane faster in a sense. There will be another method of calculating the tangential plane, and that makes use of the idea of a normal vector, of a gradient vector. And I'll go through that in the next video. So I'll see you in the next video. That's all for this video. Bye.